The Eye and Optics screencast. If you Google the human eye and select images, you'll find tons of pictures of the eye with the parts labeled. There's several in this PowerPoint, including this picture, and this picture. Let's focus on this last one because it's what appears in the tutorial. Okay, let's start with the front of the eye, or the outer part of the eye that you can see. The outermost layer here is known as the cornea. The cornea is the window of the eye. It provides protection and it provides strength, and it's also the first lens in the eye that has to do with bending and refracting light. Right in here is the aqueous humor. It's a fluid-filled space between the cornea and the iris. The iris right here and right here is the colored part of your eye. It surrounds the pupil and controls the size of the pupil. This opening in the iris is the pupil. Behind the iris and pupil is the lens, which is the second and official lens in your eye, also responsible for bending and refracting light. It's actually responsible for the fine-tuning and focusing, and it does this by changing shape. Next, we have this vast space of jelly-like fluid-filled space called the vitreous humor. It fills the space between the lens and the retina. The retina is this inner layer of the eye, and we focus a lot towards the back of the retina where the image is focused. So when light comes past the cornea, through the pupil, to the lens, to the back of the eye, and the back of the retina. In the back of the retina, there are very sensitive nerve cells. You may be familiar with the cells known as the cones and rods, which exist back in this area. Cones, like their name, are cone-shaped cells in the retina, and they are for seeing color. Rods, on the other hand, are rod-shaped, and they're responsible for night vision or vision in the dark. They are not color sensitive. The layer after the retina is called the choroid layer. Finally, the outermost layer, the white of your eye, is the sclera, and the sclera is also for protection and structure. At the back of the eye, exiting the eye, is also the optic nerve. The space here where the optic nerve is also called the optic disc or blind spot because there are no rods or cones. Okay, let's take a quick look at the human eye and vision. The main structures in the eye responsible for eyesight are the iris, pupil, cornea, lens, retina, and optic nerve. The retina has photoreceptors. There's processing time. It's very sensitive. It's where the rods and cones are, and it's where the image is recorded. Focusing is done prior to the light getting to the retina by two lenses, the cornea and the eye lens. This slide shows how light that's reflected off an object comes through the cornea to the eye lens, is bent once again, and forms an image on the back of the eye. The cornea, the front surface of the eye, does most of the focusing because the cornea air surface has a large change in the index of refraction, so the light bends a lot. The eye lens provides adjustable fine-tuning on the focus, and the image is focused on the retina. And notice it is focused upside down. The eye lens and accommodation. Muscles contract, ligaments relax. There's more of a bulge, more bending power, and a shorter focal length. If the muscles relax and the ligaments contract, there's less bulge, less bending power, longer focal length. The retina is the sensor of your eye. The images focus on the retina upside down, and the optic nerve adjusts the image in the brain. Its layers do three things: provide blood and nutrients, absorb light and convert it into an electrical signal, the photoreceptors, and transfer the signal to the brain through the optic nerve. So the path of light, the light comes through, it goes through this plexiform layer of nerve cells, it goes to the rods and cones, which are the photoreceptors, through the choroid blood vessels, and then it will go out through the back of the eye through the optic nerve. Here's a more visual cellular structure of the retina, light coming through, the nerve cells, the photoreceptors, the rods and cones, and you can see the shapes of the rods and the cones here more clearly, and through the choroid out the back of the eye. Here's a closer look at the photoreceptors, rods, and cones, and you can see their distinct shape. On to lenses. A lens is any transparent material that refracts light rays in such a way as to form an image. They can be thought of as tiny refracting prisms, each of which refracts light to produce their own image. When these prisms act together, they produce a bright image focused at a point. In addition to making distant objects appear nearer, like in telescopes, they could also be used to make small objects appear larger, like magnifying glasses, and blurry objects appear clear, as in corrective lenses. Concave lenses. A concave lens is a lens that possesses at least one surface that curves inwards. It is a diverging lens, meaning that it spreads out light rays that have been refracted through it. A concave lens is thinner at its center than at its edges and is used to correct nearsightedness, myopia. Convex lenses. A convex lens is a lens that possesses at least one surface that curves outwards. It is a converging lens. A convex lens is thicker at its center than at its edges, and it is used to correct farsightedness or hyperopia. Here are some pictures of lenses. The one all the way here at the left is convex. Convex lenses must have at least one surface that bend outwards. This is a biconvex because it has two. This one has one convex lens, one straight edge. This lens has one convex side and one concave side. This one is known as a meniscus, and we've seen meniscus before when we've done measurements in graduated cylinders. This lens is a plano concave. One side is straight, the other side is concave, and here's a biconcave. Both sides are bent inwards. Now onto mirrors. A mirror is a smooth, polished surface that reflects light rays and causes images to be formed. Mirrors can be used to view objects that are out of the line of sight, to increase illumination, to focus light or heat, or to form enlarged or reduced images. In everyday life, mirrors are used for such things as looking glasses and headlight reflectors. Mirrors are used in instruments such as microscopes and telescopes as well. The law of refraction. The law of refraction says that when a ray of light hits a surface, it bounces in a certain way. There are two types we'll consider. Diffuse refraction is when light bounces off microscopic grooves, scatters light, and the object is observed. So we saw this back when we're looking at wavelengths and why we see objects of certain colors, because some wavelengths reflect off that surface. But on smooth surfaces, there's something called spectacular reflection. Light is not scattered. It reflects without disturbing the incoming image. A little bit more on lenses. Here are how lenses might appear in telescopes. Notice these apples are the same. Here are the light rays coming to the eye, and because only this small part is making it, the apple appears very small as an image. Same size apple. Through a lens, it bends the light, and now we have a new focal point. All parts of the light are making it to the eye, and we see a larger image. This is just some more information on how corrective lenses work. When you are nearsighted, so you can't see far away, the light focuses in front of the retina, and the concave lens fixes that so that the light focuses on the retina. When you are farsighted, when you can't see close up, the light actually focuses behind the retina. A convex lens fixes that as to focus it on the retina.